So next, we will talk about independent set, large independent set. As we all know, independent sets are the sets of vertices which contains no edges. And we have learned about some theorem that gives the relationship between the average degree of a graph G and the size of an independent set. So if G has average degree E, and this is an n-vertex graph, then what do we know? We know that its independence number is less than over t plus 1. Excuse me. So we know this. This comes from the Turan theorem. The Turan theorem is about the size of click in a given graph. And you can actually flip the Turan theorem and you apply the Turan theorem on the complement of this graph. So you consider complement of G and then apply Turan theorem. And you can guarantee a click of certain size that corresponds to the independent set in the original graph. So that's you get this. And if you use this, then we can get some bounds on the off-diagonal lambda number. So let's consider the lambda number where you have two numbers which are asymmetric. Let's say first one is fixed at 3, then second one is fixed at t. What does this mean? This means that if you have n vertex graph, you want to color the edges with red and blue so that no red triangle and no blue click of size t. And simply you can, this is same as simply considering a graph which consists of the only red edges and then blue edges are not there. Then this coloring, I mean, let's say lower for, if you have a graph coloring where there are no triangle and then no independent set, no click of blue color, and that corresponds to the graph here whose independence number is more than triangle free. So how do we find the upper bound on this? So let's say you have a graph and this graph is triangle free. If this triangle free graph has average degree t, then there exists a vertex whose neighborhood at least t vertices. So this forms also, this is triangle free graph. So this vertex neighborhood does not contain any edges. So this is an independent set of size t. Okay. Also, Turan theorem said that it has independent set of size n over t plus 1. Then what does this mean? Then it contains an independent set with a size one of these. And no matter what t is, this is at least like square root of n. I mean, knowing that to be safe, let's say, square root of n minus 1. So then what do you know? If this is bigger than t, then we get a independent set of size t, showing that we get the upper bound on here. That means when does this become at least t? When n is t squared. So this shows an upper bound like this. So we know some, bounds on the size of a large independent set, and you can use it to get the upper bound on this lambda number. The question is, can you do better? If you see, this bound comes from the fact that this is triangle free. But this bound, it doesn't care about triangle freeness. It just comes from the Turan theorem. And natural question is, can we do better on this if we know triangle freeness? So this bound is actually tight. So we know that the equality holds if P is disjoint union of k sub t plus 1. Then you cannot do better than this. However, this contains lots of triangles. And if you try to come up with other example, which is close to equality, then you will also see lots of triangles. So maybe one can expect to actually improve this bound to a bigger number if this is far from this example, meaning that if this is like a triangle free. And indeed, that's how we get the better upper bound on the Lambda number. Italian Komrossi and Femoredi in 1980 proved that the RST is at most some constant times t to the s minus 1 over log t to the s minus 2 or fixed s at least t. So this constant is depending on some function of f times this, and we grow t. We let t grow. Okay. Later, Shearer in 1991 improved the, better constant. So when s is 3, what does this give? T squared over log t. And Shearer actually proved that we can even get a better constant for the triangle case. It's 1 plus 3 to 1 times k squared over log k. And how did he prove is by proving that if you have any n vertex triangle figure, G, it satisfies that it contains an independent set which has size n times log t divided by t. And essentially it's constant in front of there. It is what? 1 minus 3 log 1. So this is quite, much better result with a better constant. And indeed, it improves this bound by log d. So roughly log d is multiplied. So you would get the size log d larger independent set than usual by using triangle freeness. Okay, so let's prove this. Instead of this, let's prove a weaker one because proof is simpler. Essentially, idea is similar. Idea is same, but it's a bit simpler. So if this is an n-vertex triangle-free graph with say maximum degree d, when we apply these results to Ramsey number here, instead of every degree, you can write it as a maximum degree because still you find such a vertex. If it's at maximum degree t, then there exists a vertex whose neighborhood size is t. So in the application, it doesn't have to be at every degree. So this is already sufficient. Then this bound hold. So the constant is a bit worse. So instead of 1, here you have 1/4 and then the different log. So it's different constant smaller than 1. But let's prove it. But essentially, what it used is we will choose an independent set I uniformly at random from all independent sets. So you consider all possible independent sets in G, and then we choose one of them uniformly at random. You can simply imagine that we will count all the independent sets. Because, probability is same as just counting here with the disk distribution. Anyway, and then what we will do is that we will compute the expected size of this. So what's the average size? And then we will show that this is at least, this number. So that's what we will do. And how do we count it? So simply this is what? The sum of the all vertices. Over all vertices, you can consider the probability that a vertex belongs to I. And this is the expectation. And that's one way to write it. And another way is that for all vertex, you consider neighborhood of this. So if you have U, and then you have this neighborhood, and then outside. And what do we know? Because we know that there are at most D neighbors of B. What you can simply do is you consider the probability that the U is in I, and you divide by T, and then you add. And what happens is that for specific vertex U, let's say this has degree D of U, then in this expression, the probability that the U is in I is added exactly D of U times and divided by D. So this is added for all U. And as we assume that this is the maximum degree, so this is at most 1, so this provides a lower bound on this. So this can be lower bounded by either one of them. And the idea is that we will analyze this expression and this expression and then use the ones that provides a better lower bound on each situation to obtain the desired lower bound. That's our plan. And for that, what we want to do is you consider the neighborhood of B, and here, then if you think about it, whatever happens here, so even if you say that, okay, these vertices are included in I, that and what happens here are kind of disconnected. So, okay, it's not entirely like independent. So what's happening here could affect here, but we can analyze how it's affecting the probability that B is in I. So assuming something happens here, and then now we will analyze, oh, okay, assuming conditioning on this happen, what's the probability that B is included in I? For that, you fix a vertex B and let H be the graph outside here. I mean, in G, we delete the vertex B and its neighborhood. And let's say S is the random variable, which give you that, okay, S is exactly chosen in here. So I is the random independent of that. And then assume that these are exactly chosen. So that's the diff F. Then let's say X are the ones that has some probability or possibility of being chosen, meaning that this part is an X and this will be X, meaning that the X is out of neighbors of B. You delete the ones that's adjacent to F. So here we know for sure these are in I, then this cannot be in I, because if we add this, then I is no longer independent. However, this, they can be in I. Okay, so note that this depends on F. So all of them are actually random variables. So what happens if we condition on this F? Then we know that the vertices in the neighborhood of S are not in I. These X are the vertices in X are the ones that have possibility of being in I. That's it, triangle flip. But we know the neighborhood of B is an independent set. So we can analyze what happens in here. So what can happen here? So either B is in I and then X does not contain anything, or B is not in I and the X intersection of Y is say some Y. X intersection of Y is in some Y. This Y is what? Or any subset. Okay, two possibilities are all there. And you can even count So in this case, what? We get the independent set S union with B. In this case, we get the S union with Y. Y. And how many Y's are there? Y can be any of 2 to the X choices. So we can actually count all possible independent sets which have exactly S vertices, S chosen here. Then how many of them are there? 2 to the X plus 1 vertices. So once S is fixed, then for any subset Y, we have that the probability that B is in there, assuming this case, and the probability that the I intersection with X is Y, conditioning on this, are have the same probability, and the probability is actually this 1 over 1 plus 2 to the X, the size of X. Okay, so that gives us the information about this. And as we mentioned, now we want to analyze how this expression, turns out. So for that, what? Again, as I mentioned, this is at least 1 over D times 4 P you consider, and or U you consider, and then you consider the probability that the U is in I. And what does this become? This become what? The expectation of the number of vertices in the neighborhood of B that belongs to I. But what is this? Again, assuming the independent set outside is S. So S is again chosen here. What's the expectation of the number of vertices here? As we know, there are two cases. So this case, we don't count anything. This case, we count the vertices in Y. So we have to consider all possible subsets of Y, subsets of X. And then for each case, you have to add this. And that's what. It's simple computation, and that's exactly X over 2 times 2 to the X. So you can write it this way, and 1 plus 2 to the X. So this we know. Okay. Then from here, you can actually get bounds on here. So now we know that we have collected all the necessary inequality. We can prove this. So let's say twice times the expectation of size of I is at least what? This is at least this, and also this is at least this. We can simply write both of them once. So for each vertices, you have the probability that the B is in I, plus 1 over t times the expectation of the number of vertices chosen in the neighborhood of B. So this provides a lower bound. And as before, this can be written as the following. For each B, you add and you consider all possible S. So once you have S is a independent set in G minus and V. So for all possible choices you added, then the law of total probability said that you multiply the probability that you actually get this S. So okay, maybe it's a bit confusing. So let's write it as S prime. So S is random variable and S prime is specific set. Out of all specific set, you compute this probability, and then for that F prime yields the X prime, then what do you have to write here? So probability that the B is in high, assuming this plus the expectation of what and B intersecting with I. Again, the conditioning on the choice group. I intersecting with BH with S prime. So you can write it this way. So this is raw total probability. And what? We know this. So V S prime. And each of them, we have a lower bound. So one of them is this. 1 over 1 plus 2, say X prime, where X prime comes from S. So B, its neighborhood, you know this S prime specific choice, its neighborhood, then the remaining thing. So N of B minus the neighborhood of X prime is X prime. Plus 1 over T times what? This one. X prime and 2 to the X prime minus 1. Or 1 plus 2 to the X prime. Times this probability here. So we know that this sums up to 1. And then something is multiplied. So let's say this number, it sums up to 1. Say this whole number sums up to 1. And let's say you multiply 2 here, 3 here, 4 here, 2 here. Then the sum is at least 2. The smallest number you multiply will be give you the lower bound. Then what? So out of all this S prime, you consider when do you get this smallest? As this only we care about the size of X. So we can simply just take the minimum one. So minimum X, which give you the minimum of this. And you are what? Simply adding over all B. So you can just write N over 1 plus 2 to the X plus 1 over D times X 2 to the X minus 1 and N over 1 plus 2 to the X. And we have this 2, but we don't know which one is bigger. And I mean, just as we are not aiming for obtaining optimal constant, Let's just take the bigger one out of these two. And this is the lower bound. Then we can actually see that say if x is smaller than say x0, let's say x0 is what? Log 2d minus log base 2 log base 2 2d. In that case, what? n plus 1 to the 2 to the x is bigger than, in this choice, what do you get? 1 plus, say, 2 to the d log 2d. And that gives you what? This is at least 2d and log d n. So this lower bound. And for x bigger than this x0, and the second term gets bigger, what do you get? X times 2 to the x minus 1 n over e 1 plus 2 to the x is what? It's roughly 2d xn, and x is bigger than that, so this is bigger than what? n log d over 2d. So this shows that no matter what x is, the bigger one out of these two is at least as size is, so we get this inequality. As we start from 2 times this, so you just divide by 2 on both sides, and we know that the average size of this independent set is at least log 2d over 4d times n. I mean, of course, you have to multiply 1 plus little 1 in front. Okay, so I mean, Scher's lemma can be proved using similar idea, but more, I mean, you do the slightly further analysis and then computation, then you get the Scher's lemma. You can get the better bounds here. Okay, and okay, maybe it's good to break the video here, and then I will talk a bit more about what it implies, and then, what further research have been done in this direction in the next video.